time here by writing it in the standard form, m dx plus n dy equals 0. Okay, so this is our m, that's our dx coefficient, and that's n, okay? Okay, is it exact? Well, we have a necessary sufficient condition for exactness. Just crank out these two derivatives. What's the partial of m with respect to y? 2x, right? It's easy to do. And again, if I do any of these derivatives, I'm doing them rather quickly, and you can't follow it, you have to review, right, your partial differentiation. I think that's fair. I can't take class time to do that. And the partial of n with respect to x, actually it's a total derivative in this case, is just 2x. Great. 2x equals 2x everywhere, so the equation is exact everywhere in the xy plane. Okay, remember what exact means now. I don't want you to have to memorize the thing. I don't like memorization, okay? We know basic, this is the thing you have to memorize something, I guess. You know, you do your dm dy and dn dx, it's exact. What does that mean? Just think. Well, that means that 2xy dx plus x squared minus 1 dy is the differential of some function u, right? What's the u? You know, partial u partial x dx, partial u partial y dy. Therefore, I have to find a function u that satisfies what? Partial u partial x is 2xy, and partial u partial y is the dy coefficient, which is x squared minus 1. Right? That's the only way that can be a total differential of u. Okay? Okay. Now, it doesn't matter which one you take. Take the easier one to integrate. In this case, it's kind of the same. Let me integrate this guy with respect to x. And remember, integrating with respect to x partially. So I have to remember, I don't get a constant of integration. In this case, I get a function of y. Okay? If I were to integrate this guy with respect to y, then instead of getting a constant integration, I get an arbitrary function of x. But you'll see at the end, do it both ways, you'll get the exact same answer. So if I take this guy and I integrate, let's integrate this guy, okay? I get u equals, okay? Remember, I'm integrating partial with respect to x, so just the y comes out. What's the integral of 2x dx? It's x squared. So I get x squared y plus an arbitrary function of y. That's it. If you don't remember that, you'll never get the right answer. Very important. And what I suggest that you do is after you integrate, differentiate again, make sure you did it right. What's partial u partial x? 2xy plus, the partial respect to x of a function of y is 0. So it matches. Okay. Now, of course, now your job is to get phi of y, right? Well, how can I get phi of y? I have more information. I know partial u partial y. So now I just crank out partial u partial y from this expression. So I'm going to get x squared plus phi prime of y. Okay? But I know partial u partial y right over there. It's x squared minus 1. And this is something which I want to pause over here, tell you something which is very good as a self-check. Just like we had in the general proof. If you come to this point, okay, where you have a function general of x and y, phi prime of y, and on the right-hand side you have some other stuff in x and y, it better come out that all the x stuff has to cancel out. If you end up with phi prime of y is a function of y and x, it means you made a mistake. So it's a very good thing to pause at that point. What I see a lot of students do, they'll get phi prime, they made an error, and they'll have phi prime of y is a function of x and y, and they integrate that partially with respect to y. That's not right. This is d phi dy. It should be only a function of y. So again, if at this stage when you solve for d phi dy, if you see there's an x dependence in there, the theory tells you that you made a mistake. It's never going to happen. We proved it back over there. So you notice how nicely the x squared stuff cancels, and then we get phi prime of y is equal to what? Minus 1. Right? Which means phi of y is minus y. Okay? So, what's the u that was after? Okay? Here it is. It's x squared y plus my phi of y, which is minus y. Okay, that's u, but you can't stop here. The whole idea was solve that differential equation. And the solution to the differential equation is u equals constant, or x squared y minus y equals an arbitrary constant, c. In this case, actually, we can actually solve x squared minus 1 times y equals constant, so y equals an arbitrary constant over x squared minus 1. I was just going to have asymptotes at plus or minus 1. Okay? And you can actually go over here, take dy dx, and show you can convince yourself that it satisfies that differential equation. Okay? So again, let's recapitulate because it was such a simple example. Okay, we started off with something dx, something dy equals 0. The first thing you do to see if it's exact is you just calculate the partial, and be very careful, it's partial and partial y. Take the dx coefficient, don't take its partial with respect to x, but with respect to y. Take the partial of that guy with respect to x, they're equal. Well, now I know it's exact. So I know there's just a function u, that thing is just du. Well, du is partial u, partial x dx, that's how I got that, and partial u, partial y dy, okay? Then you have these two first order partial differential equations. Take the one which is ever easiest to do, appears to you to be the easiest. I took the first one in this case, and remember this is a partial integration, so that's how we got over here. We make believe that y was fixed, and the integral of 2x dx, of course, was x squared, and don't forget the arbitrary function of y, okay? How do we get the arbitrary function of y? We have more information, u dy. I do that, and it should come out that the phi dy is only a function of y. In this case, it came out to be -1. Then you integrate that, you get your phi of y. Then finally go back here, you got u totally. You got the whole total, you have the entire u, okay? And the solution is u equals constant. In this case, actually you get y in terms of x. Many times we'll see we can't get y in terms of x, but it's an implicit relation, but it's a solution. So any questions on that example or on the theory in general? Okay. Okay, let's go on to example number 2 then. Okay, so like I said, you know, I don't want people to memorize stuff, okay? The only thing you have to memorize, basically, is you have a form like this, and this one equation, okay? And then you know what to do after that. Okay, let's do example number 2. This one I have a lot of because it's going to be very interesting. I think this is one where we're not going to be able to get it explicitly. Example 2. And again, remember, I'm writing this stuff in the form some jump dx, some jump dy equals 0. Many times it'll be dy dx equals a ratio of two hideous functions of x and y. So let's just put it in this form to save time. I have e to the 2y minus y cosine of xy, I'll put that in parentheses, right, dx, and what do I have here? Plus 2x e to the 2y minus x cosine of xy plus 2y dy equals 0. Boy, that's really not only, look at that, you got cosines with y's, you've got exponentials of y's, okay? There's no way you can do this, it's not variable separable, it's not linear, obviously, okay? So let me just review that again. So we have e to the 2y minus y cos xy dx plus 2x e to the 2y minus x cos xy plus 2y dy equals 0. Okay, let's see if we can, so we'll do this unless it was exact, okay? So that's our m coefficient, right? That's our n coefficient, okay? You see, if you can't take partials, like, you know, very quickly, you're going to be lost over here. What's the partial of m with respect to y? And that's what I have to do. Well, the derivative of 2y is 2e to the 2y, that's easy, right? Now here I have to use the product rule, be very careful, because that's a function of y and that's a function of y. Differentiating that guy, I get minus cosine of xy, right? Y, nice cos xy, and then we have minus y times derivative of cosine, which would be a plus y, sine of xy, and the partial of that respect to xy is an x. Be very careful. Again, you get 2e to 2y, and here I use the product rule. So I get minus 1 times cos xy, and then negative y derivative of cosine, that becomes a plus sign, and then differentiate with respect to y, I get x. That's partial and partial y. Okay, let's crank out the partial of n with respect to x. Okay, well that's easy. That becomes 2e to the 2y, right? Because the root of x is that. And again, now I have to use the product rule. So doing x through, I get minus cosine of xy, right? Then I get plus x, derivative of the cosine is minus sine of xy. The derivative argument with respect to x will be y. And I believe if you look at those two, they're exactly the same. Okay? So the equation is exact. Okay. What does that mean? Okay? That means that, believe it or not, this mess is nothing more than du equals 0. Okay? But I know what du is. Plus u partial x dx, plus u partial y dy. So now my job is to find a function u that satisfies these two equations. Plus u partial x is the dx coefficient, which is e to the 2y minus y cosine of xy. Right? E to the 2y minus y cos xy. And plus u partial y is the dy coefficient, and that's 2x e to the 2y minus x cos xy plus 2y. Okay, I'm going to be lazy. I'm going to say this one has less terms. Let me integrate that guy. You could do this one. It doesn't make a difference. Let's integrate this thing with respect to x. Okay? And then we'll crank down to u dy. We'll compare.
Professor, when we took the partial y on the partial m over partial y,
Yes.
didn't we also get a plus 2 because at the very end, because it would be
Wait. Partial y. No. This is partial m partial y. You're choosing
you're
the
right, yeah.
Okay. Let's take this first guy and integrate it. U. Okay, I'm integrating this guy over here. Okay. Well, remember, I integrate respect to x, make believe y is fixed. So it's e to the 2y, integral of 1 is x. So I get x e to the 2y. Right? Okay. And then remember, I'm making believe it's y, right? So I'm integrating respect to x. I get, I think it's minus, right? So I'm integrating minus y. Integral cosine would be a sine of xy. When I take the derivative of that thing with respect to x, I get a y. No, I think that's okay. Let me just see. Do I divide by y or not? Okay, minus y, the integral of cosine is sine of xy equal to x. And then y, if I can divide by y. Okay, plus an arbitrary function of y. Let's just check this out, okay? Because I may make a mistake over here. There's this thing, the sine of xy. Okay, so du dx is equal to y. I'm just checking myself. It's e to the 2y. Okay, so I got the first term. Minus, what's the derivative of that thing with respect to x? I use the chain rule. It's cosine of xy. Derivative of the argument with respect to x would be y. And that's what I have. Okay, so we're okay. I always recommend, if you do this stuff, just differentiate it to make sure you didn't forget a factor of x or 1 over x, that type of thing. Okay.
Is that
So-
near us?
Huh?
At the end of.
That's a phi of y, an arbitrary function of y. You can call it f of y, I don't care, right?
Okay, so.
Phi of y, some arbitrary function of y.
I wasn't sure if it was an E or not.
Okay. Now, we got to find phi of y. Well, we have du dy, and if I didn't make a mistake, okay, when I compare everything and I do d phi dy, it's going to be a function of y only, okay? So remember, you calculate du dy. First, you integrate this guy, and that introduces the phi of y, and then you have two expressions for du dy that you can equate. Differentiate what you just obtained with respect to y, and what you know from, because it's exact. So if I take my derivative du dy, what happens? I get 2x e to the 2y, right? So I differentiate with y, keep x fixed, and your e to y is e to 2y times 2, respect to y. Then I get minus cosine of xy. The derivative with respect to y is an x, right? Plus d phi dy, plus the derivative of phi with respect to y. Total derivative. But we know what partial u partial y has to be over here. It has to be 2x e to the 2y minus x cos xy. Good. And 2y, right? Plus 2y. And notice again, all the stuff in x cancels out. And I remind you again, if you find out at the end, dphi dy depends upon x also, you made a mistake. That's the beauty of it. See, the theory guarantees that because partial m partial y equals partial n partial x, it's exact, and I showed you in the general proof that it has to be that this guy is only a function of y. Okay, so everything cancels out, and I'm left with what? Dphi dy is equal to 2y. And notice that this is a normal derivative, it's not a partial. Be very careful, don't be sloppy and write partials and d's the same way. Okay? And phi of y, obviously, is equal to y squared. Now someone, usually a student asks at this point, why don't you set phi of y, the y squared plus constant? You could do that, okay? But remember, at the end, I'm going to set u equal to a constant. So I'll have two constants, I can just absorb them together. So when you basically find your phi of y, it's not necessary to add the additive constant, because you're going to set u equal to a constant at the end anyway. Okay, so what's our u of xy finally? It's going to be x e to the 2y minus the sine of xy plus phi of y plus y squared. And of course, because this thing is exact, it's nothing more than du equals 0, u equals constant is the solution. So the solution to the differential equation, you put u equal to an arbitrary constant. X e to the 2y minus the sine of xy plus y squared equals an arbitrary constant c. And of course, if you had initial data, right, you could solve for that c, just like any first order differential equation. Let's see if I got the right answer. X e to the 2y minus sine xy plus y squared equals constant. Yes, we did not make a mistake. Okay, so logical question at this point, what the heck does this thing look like? See, before we're able to solve, and you can just sketch that, by hand, it's so easy. There's no way that you can solve for y in terms of x over here, right? You got y in an exponential, you got y squared over here. As a matter of fact, it may even be a multi-valued function for all I know. It goes like this, okay? So what I did is I think I'm going to show you a graph. I said c equal to 1 or something like that. You can take different values of c, okay? And of course, if you have the initial conditions, you would know